Okay, so I'm going to start 10.3. 10.3 is mostly about translation, which means the following in this context. If we did the Laplace transform of e to the at times a function, like little f, whose Laplace transform is big F, then the Laplace transform of little f with this e to the at on it is just big F of s minus a. There is a justification of that somewhere. It's basically just because, right, if you did f of s minus a, by definition of the definition of Laplace transform is just that it would be this, and because this is a you can just break the exponential apart into e to the negative s times t and e to the a times t, like this. And now, looking at it this way, this is just the Laplace transform of e to the at times f of t. So, yeah, we have that rule, and we can now use it to find Laplace transforms of things that maybe we couldn't have figured out before. Like this. So, let me find our chart. We always look at this chart whenever we're looking at the Laplace transform of anything. I don't see s minus, I'm supposed to do 1 over s minus 2 cubed. I could do 1 over s minus 2. I don't know how to do it cubed. I could also do 1 over s cubed using this formula. Let's talk about that. If I was doing inverse Laplace of 1 over s cubed, well, I guess that would be like if n was 2 here. So if I was doing the inverse Laplace transform of 2 over s cubed, because 2 factorial is 2, if I was doing 2 over s cubed, it would give me t squared. But I'm not doing 2 over s cubed, I'm doing 1 over s cubed, so it's just going to be 1/2 t squared. Right? Now that I know the inverse Laplace transform of that, now I can do this. So this is as if I had plugged in s minus 2 instead of s. So I'm going to use this formula where a is 2. Meaning I just do e to the at times f of t. So this is the inverse Laplace transform. Okay. So let's use that stuff to solve a differential equation. So this is a second order non-homogeneous differential equation. It's got initial conditions, and this is something that we would know how to do before. We would find the y sub c, the complementary solution, and I would write down the characteristic equation, which would be r squared plus 4r plus 8 equals 0. I would get r equals negative 2 plus or minus 2i. I'm skipping a little bit of work there, but that's what I would get. So my complementary solution, what happens when I get negative 2 plus or minus 2y? The negative 2 goes here, and the 2 goes here. So I have an exponential times a cosine, and then I would also have a corresponding one with a sine. And then, because this is non-homogeneous, I would then have to tack on the particular solution, which should be of the form a e to the negative t, because of this. And keep in mind, there's no duplicated terms here, so I don't have to multiply this by t or anything, so I'm fine. And then you always have to find A for your particular solution, and because we have initial conditions, we would also have to plug those in to figure out C1 and C2, and so we would have to do all of that. So we could do this before. This is using methods that we already know. I'm not going to do it that way. I'm going to do it with Laplace transforms. So here's how this will go. I do the Laplace transform of both sides. If you remember how to do the Laplace transform of derivatives, let me flip here. Yeah, here's the formula for doing the Laplace transform of higher order derivatives. And ours is going to be easy because for us, our initial conditions are all zeros. So when I do the Laplace transform of this side, when I'm doing x double prime, I get s squared capital X. And then according to this formula, right, I do s to the n times the Laplace transform. And then I subtract off, well, this is going to be 0. And then the next term would also be 0 because it's f prime of 0. So, yeah. Let me, just so everybody can follow it. This is what it would be. Of course, these numbers are 0. I'm just writing them. So that's the Laplace transform of x double prime. The Laplace transform of x prime would just be s times x minus x of 0. The Laplace transform of little x is just big X. And then the Laplace transform of this is on our table. It would be 1 over s plus 1. Okay, so like I was saying, this is 0, this is 0, this is 0. So what do I have here? I just have x times s squared plus 4s plus 8. Like that. So x is 1 over s plus 1, s squared plus 4s plus 8. So that's x, but that's not, again, that's not my answer. That's the Laplace transform of my answer. I still want little x. So I need to find the inverse Laplace transform of this. This is not so easy. This is not on the chart, but we have to do it. So this is now partial fractions. Of course, we should try to fully factor the bottom. As it turns out, we already talked about this polynomial, and again, this is this weird thing that comes up where it's like always the same polynomial. When we were discussing how to do this the other way, like with the characteristic polynomial, it's the same polynomial, r squared plus 4r plus 8, s squared plus 4s plus 8. I'm just pointing out that we already thought about this polynomial. We tried to factor it and we found complex roots. So let's not bother trying to factor it again. This is an irreducible quadratic, and sometimes that does happen in partial fractions. So what do? Probably everybody knows what to do with the first factor, and yeah, probably everybody knows what to do with the second factor as well. It's just maybe not quite as memorable, right? For an irreducible quadratic, you put something like bs plus c on top. I'm going to multiply both sides by the denominator. I'm going to get 1 equals a times s squared plus 4s plus 8 bs plus c times s plus plus 1. And if I put in -1 for s, I am going to get 1 equals 5a. And this whole thing goes away. So a is 1/5. And now I don't have a lot of great ideas for what else to plug in for s. If I put in 0 for s, that will at least kill the b. So let's try that. So 1 equals, this would be 8a. I know what a is. Plus, and then I guess this would just be, well, it would be c times 1. So then c is 1 minus 8/5, which is -3/5. Okay? One more thing to find, we have to find b. And I am really out of ideas for things to plug in for s, but there's only one unknown left, so when you're out of ideas, you just do something. You just plug something in for s, and we will be able to use it. 1 equals, let's see, this would be 13a, so 13 times a fifth, plus b plus c, of course c is -3/5, times 2. So this is 13/5 plus 2b minus 6/5, which is 2b plus 7/5. So 1 equals 2b plus 7/5. I would subtract 7/5, so I would get -2/5 equals 2b. So b is -1/5. Okay, so our partial fractions nightmare is over for the time being. What were we even doing? We were here. Now I found a, b, and c. My purpose was to find the inverse Laplace transform of big X. So let's return to that. So, oops, new sheet of paper. So big X is, well, it was a over s plus 1, so that's 1/5 over s plus 1. Then it was bs plus c, so -1/5 s minus 3/5. That's bs plus c over s squared plus 4s plus 8. Okay, and this is what we have to do the Laplace transform of. Or the inverse Laplace transform of. So this part is easy enough. I know the inverse Laplace transform of 1 over s plus 1. What are we going to do with this part? Let me take this and I should be able to complete the square on the bottom. When I complete the square, I'm going to write s plus half of this number. I take this 4 and put that here. Because if I squared this, I would get s squared plus 4s plus 4. I wouldn't get plus 8, that's why I need this. This is just whatever's left over to make sure that it's the same thing. So that's how completing the square works. Now, what am I going to do with the top? What I see here is because I have an s plus 2 on the bottom, I would also like an s plus 2 up here. Of course, I can't just go and change that because that has an effect, right? Currently, this would give me negative 1/5 s, which I'm happy with, minus 2/5, but I'm supposed to have minus 3/5, so there's my extra minus 1/5. Okay, so let me review what I just did actually. I completed the square on the bottom, and then once I noticed that completing the square gave me an s plus 2, that told me that I should, like, all of my s's everywhere should be, like, in parentheses as an s plus 2. And so then I realized that that's my goal, and that's how the top should look. So I make the top look that way. I put this s and I make it an s plus 2, and then I look around to see, okay, obviously I can't just do that. I have to change something else. So I have to balance something to make sure that it's all the same as it was before. Okay, but it's the same thing, and that's why I did it. So what we're going to use, and the reason why I was sort of obsessed with making all of the s's in parentheses as s plus 2's, is because we're going to use translation. If I wanted to do the inverse Laplace transform of this, meaning all I did there is I just took this expression and I replaced the s plus 2's with just s's. If those were just s's, I would be able to do it. Come on, be unblurry. There we go. And this is just in looking up stuff in the table. Where are we? Where's my table? Here we are. Yeah, because I can break up the top of this fraction. So let's talk about what would it be if I was doing s over s squared plus 4. So that's like this, or k would be 2, or no, wait, s, yeah, s over s squared plus 4. That's like this. No, this. Okay, sorry. It's like this. S over s squared plus 4. That's like this. So if that one would give me cosine 2t, I've got this minus 1/5 here, so I would get minus 1/5 cosine 2t. Now let's talk about this over s squared plus 4. And that's where I was mistakenly pointing at this one. If it was 2 over s squared plus 4, then it would just be sine 2t. But I don't have a 2 on the top. I have a negative 1/5 on the top. So this should be negative 1/10 sine 2t. This 1/10, it's like, it's first of all this 1/5, but it's also, there's times an extra half because like this one would normally have a 2 on top, and we didn't. Instead of a 2, we had a negative 1/5, and negative 1/5 is negative 1/10 of 2. That's why that's a negative 1/10. But that is not the inverse Laplace transform we quite wanted. What we want is a translation of that. We have this which is just if I replace all the s's with s plus 2's. In other words, it's like, where am I going? Yeah, there we go. It's like this. So a is -2. So, yeah, a is -2. So I'm going to do e to the -2t times this. And then for our final answer, because remember, I have to go all the way back. I was trying to do the inverse Laplace transform of this, and I said this part is easy, which it is. I just have to put the answer from this part in now. This would be 1/5 e to the -t. 1/5 e to the -t plus this stuff that we found. And maybe I'll clean it up a little bit. Minus 1/5 e to the 2t cosine 2t minus 1/10 e to the 2t sine 2t. Which, if you recall, we basically predicted the answer would be of this form. We just didn't figure out what these coefficients would be. Right at the very beginning, we said that based on, I keep flipping to the wrong, no, that was right. Based on the methods that we knew, we expected an answer of this form, C1 e to the -2t cosine 2t, and blah, 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 like that. Wait a second. Why is it? Oh, yeah, sorry, I just realized I made a mistake. These should have always been e to the -2t's. Yeah. When I applied this, a was -2, because these were s plus 2's. So this should have always been a -2. So now it's matching up. Now it's of the same form that we thought it should be. All right, I was almost worried there for a second, but I think it turned out okay. Thank you.